hear me okay? Cool. Really excited to have everyone attending at our Lightmatter HQ. You know, we just moved in 6 months ago, and we just got our lab set up recently. Today, this is our second event. This is the second InterConnect event that we've had. Last year, we hosted it in San Francisco after the OFC event, like right on the tail of it. This event today is really going to be focused on showing you our hardware. We're going to announce some new things, and we're going to show you some incredible things in silicon. 2026 as a year has been absolutely incredible for Lightmatter. We've announced so many great partnerships, Cadence and Synopsys on custom SerDes for the TSMC COUPE process, partnerships with GUC, Qualcomm, and all the rack initiatives that we're doing with our ODM partners. I'm so grateful to have all of you here. And I would say it feels like so far this year, more has happened than the last 8 years probably combined. So today, you're here to see our hardware, and I'm going to tell you all about it. Before we kind of jump into that, I want to talk about the context that we're all living in at the moment. AI is really taking off. If you look at this chart, what we're showing is the task length that an AI completes with 50% probability. Claude Opus 4.6 from Anthropic is in the top right there. That runs for 16 hours. So you've got a workload, a problem that an AI model is able to run for 16 hours on its own, and it has a 50% chance of getting it right. I would challenge you to think for a minute about anything that you could do for 16 hours consecutively and get it right with 50% probability. There aren't really math problems I can think of that I'd work on that I'd have a 50% probability on over that time scale. And what's crazy is this horizon is doubling every 7 months. So this is why we're seeing all of the sort of economic excitement, I think the revenue showing up for AI, and this is what's behind why we're excited and why AI is really kind of delivering on the promise that everyone thought that it would. But there's a challenge. There's actually quite a big challenge. It turns out that power comes online at sort of a 25-year doubling rate in the United States. Not all countries have exactly that same kind of power coming online rate, but AI is doubling every 2 to 3 times a year. So that's a very big mismatch. A 25-year doubling, 2 to 3x per year. There's a big gap here, and the question is, how are we going to kind of close this? It's not likely that we're going to be able to match what AI naturally would like to absorb in terms of power, but there may be some ways that we can make it feel like those gigawatts that are coming online and maybe terawatts are a lot more. So today, the message I really want to get across is that interconnect is the lever for AI. This is how we get more performance out of AI. It is the future of computing. Computers are going to get better because of the networking that connects GPUs and XPUs together. So you think about AI, it really, at this point, has 3 phases. I'd say a few years ago, I'd say training and inference. Now it's broken down. There's training, and there's inference prefill and inference decode. You're hearing a lot about both of these things at this point as the market's expanding. But these workloads have really different computational characteristics. They require different things of the systems. You're hearing a lot about companies going public, startups that go public, and companies getting acquired that are addressing different pieces of this challenge. When we look at inference for decode, it's really a memory-bound workload. And here, chips that use SRAM, very fast but low capacity memory, do very well. And when we look at prefill and training, these are compute-bound workloads. These are things that GPUs do extremely well. But these workloads have very, very different characteristics. And it would be surprising if there was one way to make all of it faster. So I'm here to tell you that Passage accelerates all of this, inference and training, prefill and decode. So first, let's look at training. I'm not going to tell you how it works or get into the technical details yet, but I'm just going to give you the punchline. When you look at a scale-up domain with 444 GPU or XPU racks that are linked with copper in the rack, so 4 racks, copper, 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 and copper, optics between them, and you compare that to 576 GPUs connected strictly by an optical scale-up domain like Passage, you're able to get huge performance advancements. So with 14.4 terabit per second, which matches like an NVLink type bandwidth here, 0.6 of the training time. So you're almost at cutting it in half. Now, when you go to 32 terabits, here you're getting to 2.7x improvement in the time to train. That's a very big deal. If you think about the implication of this, we have exactly the same number of GPUs. It's still 576 GPUs, but this same 576 GPUs worth of power is now training 2.7 times faster. Think about your AI models coming out every month instead of every quarter. This is what optics with passage enables. And we can look at inference. Let's talk about prefill first. So long contexts for AI models are really hard. Agentic workloads, you're hearing a ton about that. You're hearing about the CPU demand, and every company that sells CPUs is doing so well. Coding workloads, these really stress the system, these long prompts. So what we're doing is we're looking at, in this data set, scaling up to 1,000 GPUs at 4x the interconnect bandwidth. And you can actually reduce the time to first token, which is an incredibly important metric for inference, by 3x. 130,000 context window is a sweet spot for most workloads that you're running in AI. So this is a very big deal. You'll actually feel this when you're using the model, 3x, time to first token. Now, we can look at decode. So decode, what's interesting here is you're in a regime where interconnect can really make a big difference. With photonics, you can build network topologies. You can link numbers of GPUs in ways that are simply not possible with copper. Here we're looking at a HyperX topology. This is very geeky, but just trust me, it's one of the wiring diagrams for these AI clusters. And you can drive 11x improvement in interactivity. So this is a really big deal. This means that when you're looking at MOEs, mixture of experts, AI models, you're going to have significantly better tokens per second per user. This drives benefits for the companies, the frontier companies selling the models. It drives benefits for the hyperscalers who are deploying the hardware. 11x is quite a big deal. I was excited about 3x for the other two, but I think this is quite impressive. So I just want to summarize. We haven't talked about technology. I had a little bit of lingo, but basically what I'm telling you is this photonics thing is a really good idea. 3x better time to train, 3x improvement in time to train, 3x reduction in time to first token for prefill, and 11x improvement in interactivity for decode. This is all enabled by passage photonics. And there's another piece that's interesting. People always talk about energy efficiency. Oh, well, is this CPO using fewer picojoules per bit than the other technologies? It doesn't actually matter that much. What really matters is what this photonics platform is doing to the workload. So that's an interesting finding of what we've seen at Lightmatter. So there's a lot of performance on the table. There's so much money to be made with the value that photonics can deliver, and we haven't talked about any of it. So let's dive in. Let's figure out what is it about this photonics thing that's so valuable and that's driving performance for these AI workloads. So let's start with just defining what scaling is. I talked about 100 GPUs, 500 GPUs. These are scaling domains, and there are different domains. There's scale up, which is networking within a rack. Traditionally, it's been called scale up because this is what you can link together with copper. There's scale out, and this is looking down a row in a data center. Tens of racks, 500-meter type reach. And then there's scale across. And there's companies like Google and others who train AI models across campuses, across multiple buildings. So these are the three domains. And historically, you've had to chop these up because the technologies you use for each of them is very different. Let's talk about copper versus photonics for reach. So first, I'm going to show copper. You can see the yellow balls bouncing up and down the rack here. So copper is really only able to reach around a meter. So around a meter, and you can link up all the GPUs within that meter at very high speed. The GPUs in that rack feel like they're one GPU. And to programmers, they're very easy to program. It really executes like it is a single chip. But it's only a meter. And now let's look at photonics. This is data center scale I/O, 500 meters. And that means that you can take not just a rack and wire it up, you can take an entire row. So 500x in reach, from 1 meter to 500 meters, 500x in reach. So what about bandwidth? Well, we're going to get a little bit geeky here for a second and talk about units like terahertz. But if you look at electrical SerDes today, they run at something like 100 gigahertz bandwidth. This allows you to send data at rates like 200 gigabit per second per copper wire. Photonics is on a completely different level. Photonics actually operates at a wavelength of 230 terahertz in frequency space. We work in the O band. There's the C band and the O band. Within the O band, we can fit 60 to 70 optical channels spaced by 200 gigahertz. This means that we can fit something like 10 terabit per second in a single optical fiber. So if I were holding these cables, I have a copper cable in my hand. I can move 0.2 terabits in it. I have the same size optical cable in my hand, and I can hold 10 terabits. Huge difference in what you can actually get done with these technologies. But they're just cables. The experience is you plug it in here, you plug it in here. Very straightforward. So what do we really want to get to? This is actually what it will look like. We want to get to scale-up domains that are many racks. And in this case, I'm showing you 16 racks, 64 XPUs per rack. That's 1,024 XPUs in a single scale-up domain. If you work at one of the frontier model companies, you love this computer because this entire row of the data center feels like one chip and it programs like one chip. And it also gives you things like 2.7x lower time to train. So, one thing I would note really quick, we've all been talking about scale-up networking and scale-out networking. I'm not sure what you call this. Is this scale-up? Is it scale-out? For photonics with CPO, it doesn't really make sense to talk about these things. So the question is, 1,000, that seems pretty big, but how big could you go? And the future is going to require a roadmap where we continue to double how many of these GPUs, how many of these XPUs are actually deployed in a single computer. And the answer to the question of how big you can go depends on the wiring diagram. And this wiring diagram, you're in the data center, you're plugging things in. This is called the interconnect topology. If you look at companies like NVIDIA, they choose an all-to-all network, which has incredible connectivity. It means every GPU can talk to every other GPU directly. Now, if you look at companies like Google, they're doing things like a 3D torus topology. There isn't as much connectivity, but their scale-up domain is 9,000 TPUs. So NVIDIA 144 coming out soon, incredible connectivity between all the GPUs. Google 9,000, not as much connectivity, but an incredibly large scaling domain, scale-up domain. So how big of a system you can build completely depends on the wiring diagram, and there are trade-offs there. But you could imagine a future with hundreds of thousands of GPUs, of XPUs in a single scale-up domain if you make the right trade-offs in the wiring diagrams. So I figure I have you all trapped in Physics Town. I have a couple professors here, and I'm excited to have you. While you're here, I'm going to talk about BiDi. So I've been telling you about copper cables and optical cables. What's really special about photonics is that you can actually pack 2 cables worth of cable in one. So you can cut all that wiring down by a factor of 2. And here's how you do it. What we're looking at here is a cross-section of an optical fiber. They're made of glass, and the light travels into the board and out of the board. What we do is we take banks of colors, let's say 8 colors, and we label those transmit colors, and 8 other colors, and we label those receive colors, and we pack them in the same optical fiber. This is BiDi technology, and it has a huge impact on what AI data centers are going to look like, how fast you can deploy them, and by the way, it comes at the same performance. So there's really no downside to doing this incredible advancement, all enabled by the physics of light. So I think you might agree at this point that photonics is pretty great, that this is probably the future. You have 500x improvement in reach. You've got 30x improvement in bandwidth per cable. But photonics has kind of been viewed as a dongle for electrical SerDes. The roadmap for connectivity for I/O has been defined by the people who design SerDes. Great engineers, but they're not optics people. And if you look at the roadmap, it's gone from 56 gigabit per second to 112 and 224 today, and 448's in development from every top company. This has been the roadmap that optics has been tied to. And it turns out electrical systems and optical systems have really different properties. And there's different designs you would do if you knew the physics of the substrate that you're working in. So we're incredibly excited about the OCI MSA. This was a partnership announced with Broadcom and AMD and NVIDIA and others. And what they did for the first time is decoupled the SerDes Ethernet roadmap from the photonics roadmap. So now we're moving to what's known as DWDM and BiDi. I just taught you about BiDi. DWDM is multiple wavelengths per optical fiber spaced very closely to each other. And this is incredibly exciting for us. The standard was just announced in March at OFC. What's fun is Lightmatter has been building these DWDM BiDi links for 4 years. So we've seen this coming. We paid attention in our physics classes, and we knew what the right answer would be. And we're so happy to see the whole industry aligned on this DWDM and BiDi future. So here are some of our platforms. Passage with our EVK50 platform. You're here today, you're going to get to see this. Our EVK100 and our M1000 photonic interposer. These are 3 record-setting DWDM and BiDi reference platforms that you'll all get to see today. So first, let's take a look at Passage EVK50. You can see a shot of validation boards. We actually rack and stack these in our validation data center. What's inside? What's exciting about this technology? On each optical fiber, we have 16 wavelengths of light. So each fiber is transmitting 56 gigabit per second, 16 colors. That means 400 gig out, 400 gig in. Each fiber is 800 gigabit per second. So really big improvement. This looks like OCI Gen 2. Gen 1 was just announced, and no one knows exactly what Gen 2 will be, but this is at 400 gig per fiber, which we assume it'll go from 200 to 400, 800, and 1600, as I showed on the last slide. So already Gen 2, and we announced it last August in a press release, and we've been showing this platform since supercomputing last year. It's really the first OCI-type link that's been demonstrated. So we're way ahead on these DWDM and BiDi platforms. Just a reminder, this is 8 wavelengths headed out, 8 wavelengths headed in, all on one optical fiber, 800 gigabit per second. And not to be outdone, we decided to double that. This is Passage EVK100. So we built Passage EVK100 with Qualcomm, incredible SerDes 112 gigabit per second PAM4 SerDes platform that's really optimized for optics, the driver and the way that SerDes is designed. OCI Gen 2, still not announced, but this would be equivalent to OCI Gen 3, already at 1600 gigabit per second per optical fiber. I'm saying these numbers here, but I just want you to think for a second about what 1600 means. At your house, you probably have 1 gigabit per second internet connection. This is 1600 houses worth of bandwidth on a single optical fiber. It's an incredible amount of bandwidth, and it's way ahead of the market. People right now are working to get 200 gig silicon up and running, and we're at 1600 gig per optical fiber. So really, really big advancement here, and we're very proud of our partnership with Qualcomm and the excellent SerDes that they provided and the integration that we've done together. So those are really cool platforms, but there's something I'm even more excited about. Last year at InterConnect 25, we talked about Passage M1000, and we said it would be coming up later that year. Well, we had it at shows for the past 6 or 7 months. This is the world's first photonic interposer. It's a chip that's 4,000 millimeters squared, and it's the first time that the trade-off between shoreline and compute has been broken. For this first time, we're able to take arrays of 32 TSMC die, 3D stack them on top of our photonic interposer, and push out 114 terabit per second of I/O. DWDM optical links with 8 wavelengths. It supports 1.8 watts per millimeter squared. So this platform supports kilowatts of power delivery, all delivered through the bottom. You can see a beautiful SEM image of the platform here. Substrate, bumps. This is Passage. It's very thin. It's 100 microns thick. And on top, you can see the electrical integrated circuits from TSMC. So 114 terabit per second, all driven down into Passage optics and out through the fibers. Kilowatt chips supported in this. And this is really where the technology is going. Ultimately, this is what photonics turns into and where we're all going to be heading. In silicon today. So these platforms are really impressive. We're very proud of the work that we've done. But there are a lot of issues with getting these kinds of technologies into market. Fundamentally, you're going to be packaging them with GPUs, with XPUs, with switches. These are very expensive pieces of silicon. If you're going to glue optical fibers to them to give them these incredible properties, 500-meter reach, up to 10 terabits per cable connectivity, if that breaks, you can't throw away a $10,000 or $50,000 chip. And that's why we've been working on 2 technologies for how you can detach optical fibers from these platforms. We call them eClick, and let me show you eClick here. So eClick allows us to take both CPO chiplets and interposers and plug and unplug the optical fibers. This enables serviceability, and we're incredibly proud of the technology development that we've done there in getting this to work. Passage M1000 looks like a chip-on-wafer process, and so we've had to take an advanced packaging flow and get detachable fibers to work with that. So that's eClick. We've also got vClick, and I was surprised at OFC, this is what it looks like, at the level of excitement in vClick because I felt like we brought a Ferrari and everyone was looking at the tires. But what we've done with vClick is we've figured out how to use advanced packaging processes and get detachable fibers to work. Our foundry partners have been excited about the technology, the industry's been excited about it, and this really solves one of the big challenges with getting CPO to market. And you're going to get to see this today. All right, so as I've been saying, all of these platforms are in our validation labs behind me today and in our validation data center. This is what the validation racks look like, and you'll get to see them shortly. So it's not just about talking about what the future is, it's not about slides. The silicon is here, the hardware is here, and ready for you to see. Okay, so that's kind of the context for AI. It's really looking at where photonics is going, looking at some of our forward-looking technologies and road mapping. Let's talk about Lightmatter's products. At Lightmatter, we do both standard products and custom products. So we develop things that are just for the market as is, and then we partner with semiconductor, hyperscale, and ASIC companies to develop custom silicon solutions. On the passage side, our photonic interconnect, there's really 3 flavors that we work on. You have near package optics, and what you can see here is an optical engine. It's shown in gray. Here, the optical engine is maybe 6 inches away from the switch or from the GPU. The roadmap for optics, as you might see, is that optical engine first getting close to the GPU or switch, then it surrounds it, and then it goes underneath. So this is how I think about the roadmap. You're trying to get closer and ultimately to 3D stack with these chips. So NPO, this is our L20, we announced it earlier this year. CPO, we're developing these platforms in TSMC COUPE, and then photonic interposer, I just showed you M1000. And these are about to scale. You can see how big interposer is compared to CPO technologies. So let's talk about NPO. We were really excited to announce L20. We did the product launch at OFC in LA earlier this year. With near package optics, not everyone is quite ready to put the CPO inside the package. There's maybe one more jump before they commit to taking the transceiver and putting it inside the GPU or inside the switch. And that's what near package optics represents. With L20, we have a universal near package optics optical engine, and it's the first to market with BiDi technology. It aligns with the OCI Gen 1 MSA, so it's multi-wavelength and BiDi, but it's done at 224 gigs, and so it can talk to all of the existing switch and GPU silicon. It's 6.4 terabit per second per direction, so 12.8 terabits of aggregate bandwidth across 32 lanes of 224 gig SerDes. 2 lambda and 30 watts max. If you do the math, and I know the analysts in the room are already doing it, it's something like 4.6 picojoules per bit. So we're very excited about that platform. And we're incredibly excited about BiDi, so we'll talk more about that in a minute. So we're going to be actually selling this in 3 form factors. NPO, which is a chip-on-board configuration. CPX, which is an emerging mezzanine card configuration that people are thinking about for scale-up. and of course, XPO. We were a founding member of the XPO MSA. These are gigantic mega pluggables, 12.8 terabit per second per pluggable. So you're going to see L20 with BiDi technology in all of these form factors. I want to talk about BiDi because it sounds like, oh, you just cut the cables in half, but what are the implications? It's actually a huge deal. There's been a lot of press about deals that companies are making with Corning. You look at Meta, you look at NVIDIA. These are multi-billion-dollar deals locking in supply for optical fibers. It turns out optical fibers are going to go into shortage as the world ramps to optics everything. When you go to BiDi, let's look at and think about a 512 GPU scale-up domain. By going to BiDi and removing half the fibers, you're removing 150 miles of optical fiber. It's kind of crazy to think about that. I showed you 16 racks. That's 1,000 GPUs. 8 racks has 150 miles of optical fiber. That's just half of it, so the whole thing's 300. That's an enormous amount of fiber. 20,000 connectors are removed. And when you look at this and all the fiber management together, we come out at about 16% networking cost savings just for adopting BiDi. This technology mostly pays for itself. I think it's a must-have, especially in a world where there's a shortage of optical fiber. So I want to just take a second to help you visualize what BiDi would look like at data center scale. You can see a mock data center behind me. So here's a unidirectional, unidi wired data center. And now let's make it BiDi. Half the fiber. All the connectors, half the connectors gone. 150 miles per 512 GPUs. And just a reminder, that's only 8 racks at 64 GPUs per rack. So it's a really big effect. OK, we love Passage. Passage is our photonic interconnect technology, but let's now jump to a new topic. In January, we announced Guide 1 in Taiwan. Let's talk about lasers. I think they're a technology that's obviously receiving a lot of market attention, but I think that in the CPO and interposer world, they're a really big deal. They're actually equivalent to batteries for electric cars. When you go and buy an EV, you buy a Tesla, you buy an electric vehicle, the battery is really one of the principal things that you're looking for. The cost of the car is very much a huge chunk proportional to the battery cost. The range and the other metrics that you care about related to the battery. Well, photonic networks run on lasers. Not all lasers are the same. Not all batteries are the same. You think about lithium ion, you think about older battery technologies. Not all lasers are the same. Not all batteries are the same. So let's talk about Guide. Today, the way CPO is rolling out, people are developing these modules called ELSFP, External Laser Source Pluggable, Form Factor Pluggable, ELSFP. And here you can see a visualization of a switch with 16 of these ELSFP laser modules. You need 16 of them to power 100 terabit per second of optical I/O. So 16 for 100 T. And what's really interesting is lasers have progressed to an incredible degree. There are companies in the market that build 400 milliwatt lasers. Those lasers are so bright that you're right up against the power limit for single mode fiber. They burn at 500 milliwatts. So you're not going to be able to drive up the light source power density. You're going to have to build more of them. And it's going to get pretty crazy. 200 terabit switches are going to need 32 of these ELSFPs. 400, 64. And 800T, which is probably only 6 years away, something like that, you're going to need 128 of these ELSFPs. That's probably too many of these devices. We think that's probably too many. So today, we're really excited to announce Guide DR. And here it is. So this is Guide DR, the right way up. So this is a new technology from Lightmatter, and it'll be sampling in end of this year, coming out next year. So Guide DR gives 200 milliwatts per optical fiber across 64 fibers. It powers 51 terabits of 224 gig I/O. For a 100 terabit switch, you need 2 of these, just 2 of these platforms. It's replacing 8 ELSFPs, and I have one, so I can show you what they look like. So Guide is replacing 8. Guide DR is replacing 8 of these. So 8 versus 1. 2 of these per 100 T. So really excited about that. Let me hand these off to Monica. All right. Thank you. Where'd my clicker go? Okay. So it's a new form factor. You can tell it doesn't look exactly like an ELSFP. It's wider. It's a different shape. It's actually an internal light source. So it's inside the chassis. This new form factor, we're calling it the Laser Network Interface Card, or we call it LNIC form factor. It's field serviceable. It goes in the tray for the network interface card in an OCP MGX style rack. So you can look at the switch trays, you can look at the GPU trays. This new laser integrates inside. And what you're seeing here in the image is 200 terabit per second of light to power a 200 terabit switch. Incredible density improvement. You're going from 4 RU for 200T with lasers based on ELSFP modules to just 1 RU. Very big density improvement. So we're excited about GuideDR, and GuideDR is a platform that we're actually going to be selling to other companies, but it also powers L20, our BiDi technology. So it's designed for L20, Lightmatter's product, but also it's going to be powering all of the standard Ethernet switches that you see out there with incredible density. Now let's go back to DWDM and talk a little bit about OCI. So DWDM is the future of photonic networking. And I want to show you what a laser spectrum looks like. You see all of these red lines here. Here we're looking at optical power versus wavelength. This is what actual laser technologies look like today. You've probably heard about micro-ring resonators. These little devices have to track all of these wavelength fluctuations, and these are proportional. This is actually how bad it is, and the power fluctuations. These little devices have to deal with this spectrum as they're trying to reliably transmit hundreds of petabits per second in an AI data center. It's a huge challenge. And I think this is probably not the way to go if you're going to continue scaling on the DWDM roadmap. And that's why we're excited about our guide technology. Now, thinking about the roadmap for where guide goes, we're excited about GuideDR, but this is really the future. VLSP, very large-scale photonics. Lasers today are little diodes. And what lasers are going to become with Lightmatter VLSP is chips. They're going to be chips. So from single little discrete laser diodes to a chip with 128 lasers on it. This is where it's going. So you go from 1 laser to 100 or more. And one of the things that we're incredibly excited about, and you're going to get to see in the lab today, is self-healing. When a laser fails on a Lightmatter VLSP platform, we have optical circuit switching that allows you to route in a new laser and repair it. So the laser auto-detects and repairs itself. And it does that while delivering incredible power accuracy and stability. So we, instead of 40 gigahertz of wavelength drift, today we're at 4 gigahertz of wavelength drift. Those micro-ring resonators that deliver modulation, they're not having to work very hard to keep track of those laser lines. And the power doesn't fluctuate very much either. It's at about 0.2 decibels. So the laser lines don't move, the power doesn't move, and this gives us a roadmap from 1 color to 128 colors, all with this scalable technology platform. All right, so really excited about Passage and Guide and where the future is going. There are a few frontiers that are kind of being tackled on the road to delivering CPO to the world, and this is one of the really important ones. When you look at the rack design, I've been showing you visualizations of data centers. What does the wiring look like? What does the GPU tray look like? What does the switch tray look like? A bad future would be one where we let the market just randomly decide on where this goes. Instead of that, we've partnered with an array of the world's top ODMs and OCP to develop a new standard for what CPO racks are going to look like, the switch trays, the compute trays, the wiring for the rack and for the row. And we've just submitted the first version of that standard today. Very proud of the team for all the hard work on getting that done. This is one of the final pieces. So you can build the CPO, you can see it, you're going to get it in your hands today. What does the rack look like? The final frontier in getting the technology to market. So just to summarize the whole talk, and thank you for joining. We're showing 2 record-setting generations of OCI photonic link platforms, DWDM and BiDi. We announced a new LNIC form factor in our guide to DR laser These are the lasers and the new form factor that we think are going to power CPO. And we've shown you the 10-year roadmap for photonics in silicon today. Near package optics, co-package optics, and interposer. These are going to give a huge performance boost to AI, both on inference and training, 3 to 11x improvement. Remember the power shortage? If you're training, you have an AI training deployment, that 1 gigawatt can feel like 3 gigawatts. So the power shortage isn't that bad once you go to photonics for the same number of GPUs. There's one more thing that I want to tell you guys about. I'm personally building the company with my co-founders because I love computers. My life mission is to make sure that we can make computers better. We can drive a new Moore's law and continue to make progress in the journey of computing. Today, we've been focused on interconnect and lasers because that's the problem that the world has to solve at this moment. Interconnect and the light sources that power it are going to drive AI progress. But one day, perhaps in the not too distant future, a new kind of computer is going to be needed. And last year, we showed one. Last year, we published in VISE, the world's first photonic computer in Nature. And I'm incredibly proud to announce that it's now in the Computer History Museum with our Passage M1000 photonic interposer. For someone who loves computers, it's quite an honor. To me, one of the big significant data points and the way that we wrote that paper when we published it is around what happened at Google DeepMind. If you guys are all thinking 10 years ago, Google DeepMind published a paper on human-level control for AI video games. They trained AI models using reinforcement learning to beat humans at playing video games. 10 years later, on the dot, Lightmatter has a photonic computer that's reproducing all of the results from that paper. In just 10 years, we went from state-of-the-art in digital electronics to matching that with a completely new photonic substrate. Very exciting to me. So with that, I'm going to show you a very cool video. And thank you for coming to InterConnect. Thank you to the mayor for attending. Thank you all for the attendance here. And I'm excited to show you what we've been building for the past 8 years.